All right, so transformations, like I said, can apply to any function, and they do apply to any function, but we're going to look specifically at quadratics to look at how we can take the parabola, which if you remember, that's the name of that little U shape, and change it in certain ways. All parabolas are related to each other. In fact, they're all related to this guy right here. This is called the quadratic parent function. Can you tell me something you notice about the quadratic parent function?
It has one x-intercept.
It has one what?
One x-intercept.
One x-intercept. Where is that x-intercept?
0, 0.
0, 0. It also has what as an axis of symmetry?
0.
0. Its y-intercept is also 0. It's a really boring function. It's at the origin. It's the most basic parabola we can make. The reason I know this also is because this is the function that makes it. This was actually on our game before spring break, that GIM kit we played. It asked you what the quadratic parent function was. I don't think we knew it, but it's x squared. Like just a regular x squared with no other numbers. It's the most boring version of an equation that you can think of, x squared. It's the most boring parabola. But what's going to happen is we're going to take this boring parent function, this boring parent parabola, and we're going to do translations and reflections to it to create other parabolas. So a translation, we're going to write the word slide underneath there. A translation is a slide across the graph. So all we're going to be moving is the vertex. We're going to take like the vertex and we're going to go shift, shift, up, down, left, right. If we go up and down, that's called a vertical translation because vertical goes up and down. The way numerically that I would do that is by adding or subtracting some number behind x squared, behind the function. And if you notice, this graph goes up or it goes down. So that parent function hasn't moved, but you see how the blue one is either up or down? That's because we've translated it. We've added a number, so we've taken the vertex and the whole graph, we've gone bloop, scooted it up, or bloop, scooted it down. Horizontal translations occur inside the function here, so we're going to highlight this plus or minus h. We're adding or subtracting a number inside a set of parentheses, so you will have to add a set of parentheses to the square and add or subtract, but this moves something to the right or to the left. Again, we're just taking that vertex and scooting it over or scooting it over to the left. One thing I want you to notice before we leave these translations is normally up is a positive direction, correct? So if you add a number, it's going to go up. If you subtract a number, it's going to go down. But all of the horizontal translations are the opposite. The horizontal translations are inside and opposite. So we write HIO, H-I-O, horizontal, inside and opposite. They're inside a set of parentheses and they go the opposite direction. To go to the right, which is typically a positive direction, you're actually going to subtract numbers. And to go to the left, which is typically a negative direction, you're going to add numbers. So it's opposite. Kind of tricky.
I remember this.
Yeah. You would have done this with shapes last year on a coordinate plane, right? Moving like triangles and rectangles. Yeah, it's the same thing. We're just moving, instead of a triangle rectangle, we're moving a parabola. The last type of transformation we're going to do today is called a reflection. What does the word reflection mean? Does anybody know? It's a mirror. It's a flip. That's exactly what's going to happen. We're going to flip these parabolas. We can flip it over the x-axis by putting a minus sign in the very front, which means it goes from a happy parabola to a sad parabola. We've kind of talked about this before, where if you make it negative in the very front, it makes it a sad parabola. You can also reflect something over the y-axis, and with quadratics, it doesn't really look any different, because if you notice, that parabola is like sitting right on top of the other parabola, right? So a reflection over the y-axis for the type of functions we deal with in Algebra 1, you're going to see no visual change. But in Algebra 2, you're going to see more changes because you deal with what are called odd functions. So this transformation is really to prepare you for next year. We won't see this one very often in this class. Okay? Open this up. We're going to go to the inside and actually do a few of these transformations ourselves. We're going to take it easy today, go one by one. Our first transformation is a vertical translation up. So I have drawn the parent function for you every time. It's positive, it's a happy parabola, it goes through the origin. What does this vertical translation up tell me to do? with all of those coordinate points on my graph? Add how many?
1.
1. So I'm going to move it up 1. That means I'm going to take this vertex right here, and instead of putting it here, I'm going to move it up 1. These other points, I'm just going to move them up 1 spot. And that is going to be my new parabola. I have vertically translated it up. Scooted it up, basically. Shifted it up. That's it. And again, the number is behind the entire function. So we see the +1 at the very end. What's going to happen with that second example?
Down.
It's going to go down. How many times is it going to go down?
4.
4 times, which means every single one of those points, you're going to count down 4 units to do a vertical translation down. We see that -4, very good. So from the vertex, 1, 2, 3, 4. From all of the other points, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then I can play connect the dots, making a nice little parabola. Now let's go left and right. Horizontal translations are to the left and to the right, but remember they are kind of misleading because to go to the right, which is typically a positive direction, we're actually going to subtract numbers on the inside. Because remember, horizontal is inside and opposite, which means a minus goes to the right. We're going to move every single one of those points to the right how many times?
3.
3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 2, 3. And 1, 2, 3. And voila, I have horizontally translated the graph to the right. I've just taken that parabola and gone, bloop, shifted it to the right. Now the very last one says horizontal translation left. And why do I know it's left? If I look at these equations, what shows me that this is going to move it to the left? It changed to addition. It's addition on the inside. And horizontal is inside and opposite, which means if it's inside the parentheses, which it is, it's going to go the opposite direction. So plus is actually going to go to the left. How many times am I going to move that points to the left? 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Oop, a little bit off screen. 1, 2, 3, 4. And voila, I have translated my graph to the left 4 units. So I've just shifted all of the points. It's really easy to tell the vertical and horizontal translations by just looking at the vertex. It should be at 0. And if it's not at 0, how much did it shift over or how much did it shift up and down? That'll be our horizontal translations left and right. Now we have our reflections here. Okay, the first reflection says reflect or mirror over the x-axis. So right now I want you to kind of color in your x-axis. Just give it like a little, oh, yeah, right there, like that's perfect. Okay, we want to reflect or mirror every single one of those points over the x-axis. And we know we're doing this because we have negatives in front of the x squared. Okay, so I'm going to take that point right here and I'm going to mirror it over the x-axis. Ends up being right on top of itself. I'm going to take this point right here and mirror it across the x-axis. I would jump down 1 time to make it to the x-axis, which means I jump down how many times below it? Just 1 more time. For this coordinate point, I would have to jump down 1, 2, 3, 4 times to make it to the x-axis. So I go away from the x-axis 1, 2, 3, 4 times, mirroring that point across the x-axis. And I do that for all the points. And then I have my sad parabola. So reflections over the x-axis make our little sad parabolas. But reflections over the y-axis, like I said, we're not going to see that often because when we highlight, bless you, the y-axis, and we reflect the points over the y-axis, I'm going to move this point 1 unit to make it to the y-axis, which means I move it 1 more unit, which means it's here, and vice versa. And if I move this point to the y-axis, I move 2 times, 1, 2, which means I go away from the y-axis 1, 2 times, and vice versa. Guys, look, it ends up being right on top of the actual parent function, Nothing has happened. There's no visual change. That's because in the actual function itself, there is no visual change.
So you don't change it at all?
Not for this function. In Algebra 2, when you deal with odd functions, there will be a visual change, but this is called an even function. It's symmetrical about the y-axis, so when you flip it, it lands right on top of itself. There are other functions where that's not the case. We just don't study them in this class. So we won't see this one very often just because it doesn't really do anything for a quadratic function. But it does something for other functions, so don't count it out for later. But for now, we don't really need it. Okay, so one of the ways that I would answer this question is looking analytically at the equation. It says, given a function rule of graphical transformation of f of x equal x squared, that's the parent function. We need this, so circle this right now. That's the parent function. Write the verbal description for g of x. I want you to identify what vocabulary has happened to this graph. The first way I would do this is look analytically at it and decide what's happening. We are changing this function by adding a number on the inside. What did we say was the thing that happened when we added a number on the inside? It's inside. Is it horizontal or vertical? Horizontal. So we could put an H for horizontal. I'm okay with that for short because horizontal is way too long to write. And is this it's gonna be a translation. That's the vocabulary word. It's gonna slide. So horizontal translation. Now, which direction is it going to move? To the left or to the right?
To the left.
To the left, how many units?
4.
To the left, 4 units. Analytically, I know that's what's happening because the equation tells me that's what's happening. I can also be a visual thinker and use a graph to answer this question. I would go to Desmos and I would graph both the parent function and this f of x, or g of x function, and see what they look like. Let me show you what that means. Once you confirm on the graph that it does actually move to the left 4 units, you're done. I just need the vocabulary here, the verbal description of what's happening. It is a horizontal translation left 4. Yes? I want to give you some time. I want you to at least try to get through number 8. If you feel like you can go to the next little section with your star partner, you can. Don't leave your star partner behind, though. This is your star partner. You got him. All right, here we go. Y'all get started on these. Just so I know most of you checked your work with your star partner and or a graph, I'm going to go ahead and start putting the answers up here for the first little set so you can see how you did. How'd we do, folks? Are there any we want to go over? The last 2? Okay, yeah, the last 2 have a lot going on there. They have 2 numbers affecting the transformation. They have 2 numbers added to the parent function. Both of those numbers are going to do something to the graph. But they do exactly what we've always done. If the number's inside the parentheses, it's going to be moving horizontally. If the number's outside of the parentheses, it's going to be moving vertically. We just have 2 things at one time. So what's going to happen in a graph, which is pretty cool, and I'll show you here in a second, is that you're not only going to move side to side or up or down, you're going to move almost diagonally, going side to side and up and down. Let me show you. Awesome. I know some of us moved on to the second analytical side. We're going to work backwards now. I'm going to do the first one with you, and then I want you to try to do the other ones. Number 5 and 6 are a stretch, but I think you can figure it out. No. It says the graph of f is translated 7 units to the right to create the graph of g. We want to write the equation for g, comparing it to the parent function. For sure, it's always going to start off with g of x equals. We know that part. Woo, it's a g function. They said to name it g. We got that part. It says to translate it 7 units to the right. Is 7 units to the right going to be inside the parentheses or outside the parentheses? Inside. So here's my parentheses. I'll let it be inside. And if I'm going to the right, am I going to subtract 7 or add 7? Subtract 7. Boom. I just wrote an equation for this verbal description. I said take the parent function x squared and shift it to the right 7 units. That's it. Can you do the rest of them? I know 5 and 6 are going to be a challenge, but I want you to try before you say you can't do it. Let's do a quick check here and see how we did on these. On number 2, it says the graph of f translated 2 units to the left. Left is going to be inside, so we know we need a set of parentheses here. And to go to the left, we're going to add 2. Number 3 says graph of f is translated 4.5 units down to create the graph of g. Down means there's no need for there to be a parentheses, and we're just going to subtract that number behind it. Graph of f is translated 4 units up. Again, up is not one of the directions where you need parentheses, so it's just a +4 tacked on at the end.
Oh, I did this.
That also works. Yeah, he used function notation for it instead of notation without it, which is absolutely fine. You can do this. That's just the function notation version. You'll see both, which is why we put both on your notes. Okay, you'll see both. This last one, number 5, says the y-intercept of the graph of g is 5 units below the y-intercept of the graph of f. But here's where this comes in. You have to remember that your parent function goes through the origin 0, 0, which means its y-intercept is 0. If you want a graph that has a y-intercept that is 1, 2, 3, 4, 5 units below it, all we need to do is shift that graph, shift that graph down 5 units for it to have that y-intercept. So how do I shift a graph down 5 units? Subtract 5 where? Inside or outside?
Outside.
Outside. So I'm just going to subtract 5. That's it. That's the only way you move it down. But you have to remember that that parent function is boring and goes through the origin. It's also on the back wall right next to Adrian's head. That's the parent function. Number 6, last one, it says the vertex of the graph of G is 3 units to the right of the vertex of the graph of F. Again, remember, that parent function goes through the origin, so its vertex is at 0, 0. And if we want it to be 3 units to the right of the vertex, that means we want it, that's the left, 1, 2, 3. We want it to be here, which means we're just translating this graph to the left 3 units. That means it's on the inside. I said left, I definitely meant right, my bad. So that's inside. Inside stuff is the horizontal. Left and right goes inside, up and down goes behind. Any questions before we move to the back page? In fact, I actually want you to ask me one question. It can be about anything on this front page of this classwork. Speaking of, is this going to be on the star? Here are some questions that were on the star in regards to transformations. A lot of the questions on the star happen to ask you it in a graphical way or in a way that you can make it graphical, which is nice. This first one says the graph of a quadratic parent function f was transformed to create the graph of g of x equal f of x plus 2 plus 4. Which graph best represents g? Is that the right? Oh, yours says plus 4 plus 2. I made a mistake on mine, so let me edit real fast. I edited yours and didn't edit mine. Oops. Is that right? Is that what y'all says? Mm-hmm. Okay, great. Okay. Which graph best represents g? Okay. First of all, they didn't tell us what the parent function was. Do you remember what that equation is? F of x equal to x squared. We have to kind of memorize that. I believe actually that is on your vocabulary list we gave you. It's not until the back side, I don't think, but it is something I'm going to need you to know. Quadratic parent function is f of x equal x squared. You look for that x squared every time. Now, if we wanted to answer this graphically, we'd have to know that fact, but if we just remembered the definitions that we learned today, we'd remember what this number tells us to do and what this number tells us to do. What does that red number on the inside say my graph should be doing? Which direction should it go?
To the right.
If it's plus, it should go to the left. So left 4, and then how many up? So we're just looking for a graph which vertex from 0, 0 has moved left 4 and up 2. Did that letter A move left and up? No. Letter C, did it move left 4 and up 2? That looks pretty good. We'll hang on to that one. Number B, did it move left and up? No, yeah, we don't want that one. Letter D, did it move left and up? No, like super wrong. So we know answer choice C is the only one that has moved left and up. Just by knowing these ways that you can answer these questions, these equations and how they look, we didn't have to graph this one to answer it, but we could have. You can type the parent function and type g of x into your Desmos and see this graph appear. You just have to remember the parent function because it didn't give it to you. It's pretty easy to remember. Okay, this next one is interesting. They've written a question like this on the last few stars, so we're probably going to see one like this, which is nice that we know this. It says the graph of the quadratic function j is shown on the grid. Okay, there's j. It's a parabola. It's a happy parabola. Okay, cool. If p of x is equal to x squared, that means that this is the parent function. So I'm going to fake draw a parent function in because I know it's like right here. There's my fake parent function. And j, which is what's graphed here, is p of x plus n. That's this right here. What is the value of n? Okay, so this is a very confusing way to ask. What transformation has happened to that green graph compared to the parent function? Where has it moved? How many has it moved down? 3. So this number behind it, wouldn't that be a negative 3 to move it down 3 times? That means n is negative 3. It's a very confusing way that they ask this question. Yes, sir?
Still the same thing like this.
That is still the same thing. So he put negative and then he put his 3 over here. That is still fine. In high school, you can pick where you put your numbers. I always put mine on the left side, but you can do whatever you want. I would rather you not put it in the middle. Pick one of the sides, please. Left or right. Don't do the middle. Don't do the middle. It's just potential for you to accidentally bubble it incorrectly. So to make it easy on yourself, left or right only. Okay? Now, if that's the case, we just answered this one. I want you to go down to the bottom. The very last question on this page was another question on another star one year. I want you to answer this one. Talking about if p of x is equal to x squared, remember that's the parent function. They didn't draw it in, but I can. Here's my parent function. How does this j of x function compare? How much did it move down?
4. More than that, like 5.
It moved down 6 times. So the number that we would have added or subtracted at the end was negative 6. We would have added negative 6 to shift that graph down. It's not a complicated question when you understand what they're asking. They just ask it in a very particular way. You just have to make sure you know that parent function, that it's through the origin. Okay, I know I'm doing this out of order, but we're going to go over to this question right here. I love this question. I think it's so creative. It says function p is in the form y equals ax squared plus c. If the values of a and c are both less than 0, which graph could represent p? Okay, here's what I want you to do. I want you to first look through your foldy notes for a negative sign being in the very front of my equation. What happens to my parabola when there's a negative in the very front of the equation? A reflection over the x-axis, which means this should be a happy or a sad parabola. Which one can I eliminate? G. I know it needs to be a sad parabola if a is negative. Sad parabola. I also know that the c value, or the number at the end, is going to be negative. What happens to a parabola if the number at the end is negative? Look at your notes. What happens to a parabola when the number at the end is a negative number?
Oh, it's back to its red.
No, at the end, at the end.
Oh,
If it's on the outside of your parentheses, is it a vertical translation or a horizontal one?
It's, well, at the end, is that horizontal or vertical? Vertical. And if it's going to be negative, it's going to be less than 0. Is it going to go up or is it going to go down? It's going to go down. So we're saying that the C value is less than 0. That means the number at the end is less than 0. It's going to go down. Which one of these graphs that we have left has moved the parabola down? That's the only one that is a possibility here. This one has moved it up. This one had no move whatsoever. And we know that it has to be less than 0, so it has to be some sort of negative number pulling it down. So this has flipped it over, the reflection in the x-axis, and it's moved it down. Okay, last question here in the center. The graph of f of x equal x squared was transformed to create the graph of g of x equal f of x minus 9. Which statement about the graphs is true? Okay, we're comparing the parent function, they didn't call it that, but we know it is, to g of x here. Analytically, what is this negative 9 going to do to the function?
It's gonna make it go down.
Ooh, I heard to the right and go down. Is it on the inside or the outside? Outside, so it's going to move up or down, so it's going to take it down. How many units? 9. We can verify this graphically if we would like. So which answer choice talks about moving something down 9 units? D. Why is D the one?
Because it's saying that the new graph,
Uh-huh.
it moves 9 units down below the original graph.
Very good. The original graph has a y-intercept at 0, so if we move that y-intercept down 9 units, we've shifted the whole graph. We know that the other ones are not correct because it's not a reflection, so that's not the vocabulary we're looking for. We're not looking for it to go to the right, and again, not a reflection. So we can very easily get to the correct answer here, that it's going down 9, so it's moving the y-intercepts down.